In this example, we are going to investigate color proportions for M&Ms. M&M's candies originated in the US in 1941 after the son of the Mars Candy Company founder saw soldiers eating British-made Smarties, chocolate pellets with a colored shell, during the Spanish Civil War. M&M candies are manufactured at several factories in the US. The nearest factory to Pittsburgh, California is in Las Vegas, Nevada. One of the largest factories is the original factory in Hackettstown, New Jersey, where they manufacture 2 billion M&M candies every 8 hours. Here's a video link for you to watch to see how the manufacturing process goes at Hackettstown, New Jersey. M&M's candies are sometimes produced in special colors for holiday bags, but the usual colors are orange, red, yellow, green, blue, and brown. One of the employees at the factory in Hackettstown claims that all M&M's factories in the U.S. produce an equal number of each of the 6 colors of M&Ms. We will investigate this claim in our discussion questions. Since it's not practical for us to visit each M&M's factory in the U.S., we will use sample data and sampling techniques to investigate. So we are going to investigate the proportion of blue M&Ms produced in the U.S. in random samples of M&M candies, or as close to random samples as we can get. We first want to think about what types of results would support the M&M factory employee's claim. What type of results would indicate problems with the M&M factory employee's claim? So we can say if the colors are produced equally, we expect 1 out of 6 of the M&Ms to be blue. Since there are 6 colors, if everything's equal, we would say 1 out of 6. If the colors are not produced equally, the proportion of blue M&Ms would be far from 1 out of 6. So we are interested in predicting the proportion of blue M&Ms in all M&Ms. We are going to let the variable x here represent the color of a randomly selected M&M. So we want to think about, is x representing a categorical or quantitative data? So since x equals the color of the M&M, and we're going to have 6 choices for x, the data is categorical, and we will use proportions in our calculations, not means. Means would apply to quantitative data where you would have an average. So we want to describe the population that we are making an estimate about. So we are going to make our estimate about the population of all M&Ms produced in the U.S. You might want to get more specific. If you have a bag of M&Ms in front of you, you could figure out what factory it came from and say that's the population you're going to make a prediction about. So for now, we'll say our prediction is about all M&Ms produced in the U.S. So in most situations, statisticians cannot know the population proportion, but in this situation, the M&M factory employee is making a claim about the parameter, what we call the population proportion, for each color. So according to the M&M factory employee, what is the population proportion P for blue M&M candies? We will investigate whether or not this seems likely to be a valid parameter. And when we say parameter, we mean the number that describes the whole population. Since we're talking about categorical data, the parameter is a proportion of, in this case, blue M&M candies. According to the M&M employee, the population proportion of blue M&Ms is P equals 1 out of 6, or as a decimal rounded to 4 places, 0.1667. Since all 6 M&M colors are claimed to be equal, that's why we're using equal 1 out of 6 for every color. All right, so we're going to assume you have a sample of M&Ms. If we were face-to-face, I would give you small bags of M&Ms, and you could count out 10 at random. So you would think about, imagine yourself counting out M&Ms and a random amount being blue. So in this case, I said our sample proportion here, P with the hat on it, to indicate it's a sample proportion and not a whole population proportion, could be 2 out of 10 for this student, or as a decimal, 0.2. So we expect every student will have different answers here. Although some students may get the same value, we don't expect every student to get the same value. So question F asks, is the proportion of blue M&Ms from your individual sample a reasonable estimator for the proportion of blue M&Ms coming out of all the factories in the U.S.? And explain your reasoning. So we know there's variability in sampling for any single random sample. So our individual sample on its own is not a reasonable estimate. So the one sample I have here, 2 out of 10, is not enough on its own to say for sure we think 2 out of 10 or 20% of M&Ms are blue. So we expect there to be variability in samples, meaning that the proportions in a sample will differ from the parameter, but should not be surprisingly different. To get a reasonable sense for the parameter, we will use a dot plot to look at all the proportions of blue M&Ms calculated by students in a class. So here I have reproduced a dot plot from a previous class where students were able to count out M&Ms in person. In this dot plot, we see the proportion of blue M&Ms ranged from 0, meaning no blue M&Ms in their sample, all the way up to 0.5, meaning 5 out of 10 M&Ms in their sample were blue. And then we see peaks here at 0.1 or 1 out of 10 and 0.2 or 2 out of 10. Those were the most common values in this class. We use this data to build a frequency table. So in the frequency table, we are counting how often each proportion came up. So these frequency values correspond with the bar heights in our dot plot up above. I stopped the frequency table at 0.6 because it would be very, very unusual for somebody to get more than 6 out of 10 blue M&Ms. I've yet to see that in a random sampling situation. Based on the dot plot, with data from the entire class, is there evidence to support the M&M factory employee's claim? If you are not convinced that there is enough evidence, which way are you leaning? To agree with the M&M factory employee that they are correct, or to disagree? So since our proportion, p equals 1 out of 6, or 0.1667, is between the two highest proportions in our dot plot, so between 0.1 and 0.2, if we imagine where that 1 out of 6 would be, it'd be right between those two peaks. We think there might be evidence that the M&M factory employee is correct, but we are not convinced. So now we're going to think about constructing some intervals to try to give a range of possible values. So think of the dot that we graphed in the last example as a best guess if you could only choose one value to estimate the population proportion of blue M&Ms. Statisticians call your best guess sample proportion a point estimate. If you took a new sample of 10 M&Ms, would you expect to get the same point estimate again? Why not? So no, we would not expect that same estimate to come up again in most cases because we expect some variability in random sampling. So if you got 2 out of 10 this time, the next time you might get 3 out of 10 or 1 out of 10 or 0 out of 10. You expect there to be a little bit of variety and not to get the same proportion every time because we're doing random samples. Sampling variation suggests that your estimate may be close to the true population proportion of blue M&Ms, but it will not be exactly equal to the parameter. So remember, the parameter is the population value. So when we do a sample, we expect we can get pretty close to the population value, but we don't expect that we're going to exactly get the population value in our sample. So in this plot at right, students have added a margin of error to their point estimates. A margin of error is a small amount that is allowed for in case our calculation is not exactly correct due to the variation in sampling. So here is a proportion of blue M&Ms. Here on the x-axis, it's written at the top of the graph. And this ranges from 0 to 0.6. And then every student is putting a dot where their sample value was. So we see many different sample values here. And then they're extending the lines at the side to create a range of value, or what we call an interval. So there's a lower limit and an upper limit for the intervals so that it gives a reasonable range where we think the true population value of blue M&Ms might fall. All right, so for now, we're going to use 0.1 as our margin of error, and we will see how to calculate more accurate margins of errors in the next example. So on the plot from the previous example, if we were in the classroom, we'd have this plot up at the board. You're going to plot your point estimate with a margin of error extending on both sides, similar to the plot seen up above. So now we're plotting an interval of possible values, not just a point estimate. So our points are not staggered quite like in the graph above, so they're a little bit overlapping. I tried to use different colors here to extend the intervals. The points at 0 only would increase. They wouldn't have a negative part of their interval because we would never estimate a negative proportion. So we can see here our range of intervals extending out 0.1 as our margin of error. So one of the samples that had 2 out of 10 blue M&Ms would extend with their interval down to 0.1 as the lower limit and up to 0.3 as the upper limit. So what we're saying is if you picked 2 out of 10 blue M&Ms at random, you would predict that the range of possible values for the true population proportion of blue M&Ms could be anywhere between 0.1, 1 out of 10, up to 0.3, 3 out of 10. So instead of giving a single point estimate, you are giving a range of values. So now we want to draw a vertical line through our intervals where that claimed population proportion 1 out of 6 would be. So imagine drawing that through. It would go right through the intervals between 0.1 and 0.2, and then we could count up how many intervals that passes through. So I counted that 18 of our intervals contain the M&M factory employees claimed P equals 1 out of 6 or 0.1667. So we'd say the probability that we have the value in our interval would be 18 out of 26 or 0.6923. So based on the interval plot with this data from an entire class, is there evidence to support the M&M factory employees claim? If you are not convinced that there is enough evidence, which way are you leaning? To agree that the M&M factory employee is correct or to disagree? So I am somewhat convinced by 18 out of 26 intervals containing that claim. That's 0.6923 or 69.23%. So my rationale here is that more than half of our intervals contain the M&M employees estimate P equals 1 out of 6 equals 0.1667 as a decimal. So I'm going to say there is some evidence to support the claim, but it's not completely convincing evidence. For me to be completely convinced, I'd want to see maybe 80 to 90% of the intervals containing that value. So now we want to think about what factors might be affecting our estimates and what you suggest we change for the next step in our investigation. This is a small sample size. It's just n equals 10 M&Ms, so that might be problematic. So we are going to suggest investigating a larger sample size, and we will do so in the next example.